Hello, welcome to my new live stream. Today our plan is to talk about bootloaders. Okay, so the plan for today is to talk about bootloaders, how they work. We will look a bit at how some of the existing bootloaders work, like Grub or Lilo, or the Windows bootloader, and we will try to design a better one. Yeah, so first let's start talking a bit about our current bootloader and how it works. So I have this little board. Okay, I hope you can see this. Okay, so the basic plan is to... Okay, let's start by talking a bit how our current bootloader works. So the way it works is we have the stage 1. So this is a little disk that we have, right? And this is the boot sector. And that's where our stage 1 is. Now, the problem is that after the stage 1, we basically have the structure of the FAT file system. So, you know, the file allocation tables, the directory entries, so that's, and then the basic disk contents. Now, the way stage 1 works is that it tries to read all of this information from here, and it tries to basically parse the FAT12 file system to basically find our stage 2. Now, this approach has a bit of a problem. To add support for more file systems, or to add support for FAT16, FAT32, we basically have to modify our bootloader, our stage 1, which is not exactly easy to do. We have to work in assembly, and we have a very limited amount of space. We have 512 bytes, which is barely enough to do any of that. What this means is that we have to split our implementation. We basically have to use like macros and all kinds of you know, assembly like preprocessor to select which file system to pick, and that just creates a lot of complexity, and there are better ways of doing that. Okay, so let's start by looking at... we'll start with the simplest one, which is the Windows bootloader. Now, I'm not sure if they still do this, but this is how it worked in the older versions. Okay, so let's start... okay, Grub. Sorry, Windows. Okay. So I'm not sure if NTFS has this as well. I'm pretty sure it does, but the FAT file system does have a parameter in the boot sector, which basically tells it how many reserved sectors there are. And the number of reserved sectors can actually be pretty large, like 255 or something like that. So 255 divided by multiplied by 512 bytes will give us about 100 kilobytes for the bootloader, which is actually quite generous. Okay, so we basically have, same as before, we have stage 1 here in the boot sector. And then stage 1, all it has to do is just load the section of reserved sectors, and this is basically where the stage 2 is. And then we have the rest of the file system, the file allocation table, and so on, doesn't matter. Okay, now this is a great approach and I really like this approach. However, in our operating system that we're working on, we basically want to support other file systems. We want to support ext. And the problem with ext is that its structure is a bit different. Let me just show that really quick. Okay, so in ext, we basically have the boot sector, just like before. Oh no, my marker isn't working. Oh well, tried it. So, yeah, this is the... No, it's not working anymore. Okay, let me try something else. I have another idea. Okay, just give me a minute here. This is my backup solution. Okay. And now what? Oh, come on. Okay. Okay, this is my backup solution. So I'm basically using my phone here to record. Okay, so I was talking about how Grub. I was talking about how ext file system looks like. Alright, so ext2, it kind of looks like this. You have the disk, and over here we have the boot sector, just like we have on every other. But the boot sector is part of a larger structure which has two sectors in size, which is called the boot block. And after that, there's the super block. It's basically how it's called. Is my image reversed, right? Hold on. Okay, now my image is not reversed anymore. Is it looking good? Okay. So as I was saying, there's the boot block, which I mentioned, which is basically 1 kilobyte, 2 sectors. And the problem with that is that that's not a lot of space. It's really not enough to have 2 sectors. And this is the super block. Okay. So this approach doesn't work for ext2, unfortunately. And this is one of the file systems that we want to support. So let's see how other operating systems do this. So let's look at Lilo. Lilo is an old bootloader that was used by Linux until right now most distributions use Grub. But yeah, a long time ago they used Lilo. So Lilo has an interesting approach. Okay, Lilo. or the Linux loader. That's how it's called. And the way this works is that we have the boot sector, just like we had before. Okay, and inside this boot sector we have a little area which is reserved, and this is an area where the install process will basically put a list of sectors that this boot sector has to read. This way we don't depend on basically parsing a file system, but as part of the installation process we need to pass in this list of sectors. Alright, and then we have the file system. This is the super block, the boot block, then the super block, and so on. We have the rest of the file system. Now, as part of the installation process, the installer will basically look at the stage 2 file. It will try to figure out what sectors it is actually using and to fill this little structure here. Now, I think this is a great approach. It is it will work with basically every file system. There's no problem about that. However, there is one limitation here. And that limitation is that we cannot move stage 2. So stage 2 might be something like this, a block here and a block here. Basically, let's say that these two sectors are stage 2. Now, if we defragment the file system, that's gonna create a bit of a problem, because these will move and we won't be able to boot anymore. So that is a bit of a problem. This is the limitation with this approach. Okay, now let's see how Grub works. Grub is probably a bit more interesting. Now, when talking about Grub, we have to talk about how partitioning works. And there are basically two ways of partitioning disks. There is MBR, which is the older system, and there's GPT, which is the newer one. Now let's focus on MBR, because this is what we're talking about today. So in MBR, this is called the master boot record. That's what it stands for. And the way this works is that we have the disk, just like before, with the boot sector. And right at the end of the boot sector, we have basically a structure which contains the list of partitions. It has some information about where they start. So basically the LBA, or the logical block address of the start of the partition. So okay, let's just call this partition table, and this will have information like the start, the length, and some attributes like whether it is active or not. That's one of the important flags. So flags. Okay, and this partition table is pretty small. It has 4 entries. That's it, just 4 entries. And if you have ever used a partitioning tool with MBR, you will see that there are 2 types of partitions. There are primary partitions, which are in this little block here. These are the primary partitions. And there are secondary partitions. And the secondary partitions, they basically work in a similar way, but this structure here will basically be the first sector of that particular partition. Okay, so let's say that we have a little gap here. The gap is usually, in most cases, the first partition will start at sector 63. And here we have partition 1. and then some place later we will have partition 2 and so on. Okay, now same as with the MBR, this partition 1 has a boot sector of its own. Now, if you go into this partition table, okay, I have to move this a bit, okay. So if we look into these flags, there is the active flag, and that's a very important flag because that's how the MBR, the master boot record, that's how basically the software that lives here, this little bootloader from over here, that's how it knows which partition to load. So for example, let's say that partition 1 is marked as active. There's a little bit of code here, which is often installed by fdisk or whatever partition tool you're using. It usually installs this code by itself. And what it will do, it will go through this partition table and it will look for the first entry that is active. And then it will just load this little boot sector and it will pretend that that's the way it's supposed to work. Yeah, it will just load that and it will continue from there. Okay, now this is the little interesting part because Grub will basically just install its own boot sector, like on the partition that is active. For example, here, let's say that it installs stage 1. Okay. Now Grub is a pretty big bootloader and it doesn't actually fit in these 63 sectors, but yeah, it basically has stage 1.5 here, that's how it is called. In this little gap here between the boot sector and the first partition, this is where Grub stores its stage 1.5. Now Grub is a very big bootloader, so this is not enough for it. So, but here in this little space, it has enough room for the file system. It has enough room for the file system drivers, so that it can load it from the actual file system that it booted from. Alright, and then the stage 2 will be somewhere on this partition. Now this is an interesting approach, and yeah, it is a bit more complicated and a bit more involved, and but I think it works great. It doesn't have the problem that Lilo had with, you know, what happens if you defragment. It doesn't have that problem. The bootloader will be pretty stable, and this gap is actually really nice. 63 sectors. Without the boot sector, that's like okay, so we're indexing from 0, so that's 63 sectors multiplied by 512 bytes. That gives you about 30 kilobytes, and 30 kilobytes, you can do quite a lot in 30 kilobytes. I think it might be enough for what we want. So this is the approach that I would like to do. It is guaranteed. It's not guaranteed all the time, but in most cases I don't know, that's a good question, if it's guaranteed or not. Most formatting tools will basically just leave that gap there, so it shouldn't be a problem. If you format using any of the tools on Linux or on Windows, that gap will be there. Yeah, maybe some tools don't do that, but I don't know what to say. I'm not 100% sure. I need to, maybe I'll research it and answer it if I have the answer. Okay. Alright, so that's how Grub works. Now, how should we design our own bootloader? I kind of like these two approaches, basically. Now, obviously, I would prefer to use the one from Windows because it's the simplest. However, since we want to support X2, that it will not be possible. So we have to go with one of the other ones or come up with one of our own. And our options are to basically do whatever Grub is doing or do whatever Lilo is doing, or some combination of those two. Something I haven't mentioned here is that Grub will not work if there is no partition system. So that's why you don't see Grub being used for CDs or DVDs, and that's why Grub cannot be used for floppies. Now, obviously floppies are kind of old, they're deprecated, whatever, but you cannot use them on CDs, which is a bit of a problem. That's why most of the distributions will use sys Linux or some other bootloader for the live CDs. Okay, so let's try to think about a way to do our own bootloader. I kind of like this approach that Grub has because you don't really depend. It's hard to corrupt because this section should not be touched by any software basically. So it should be pretty safe. The one limitation that I don't like is the fact that you cannot use it on simpler disks that are not partitioned. And so my idea would be to try to combine these two somehow. Maybe create like a little section here in the boot sector that is part of the install process, and when we install it on a MBR formatted disk, then we can just set this these little parameters, just tell it, okay, load it from sector 1 to sector 63. And that should simplify things. Okay, should we start implementing? Okay, just looking a bit through the comments to see if there are any good questions. Yes, I do work as a developer. Okay, thank you a lot for all the support. Okay, so let's go ahead and try to implement this stuff. Let's switch to my desktop. Alright. Oh no, you saw my notes. Okay, that's not an issue. Alright, so let's think a bit about what we need to do here. Okay, so this is what our stage 1 looks like right now. Okay, so we have this, just trying to remember how it worked. Okay, showing the loading message, then reading the drive parameters. Okay, and then I try to read the file allocation table. Okay, we'll delete most of that and try to make this a little simpler. Okay. Alright, so let's get started. We're gonna have some fun in assembly, which is always the funnest fun you can have. Okay. Okay, so let's go ahead and start by removing the code, which is just fat specific. We don't need that anymore. Okay, we don't need the LBA of the root directory. And here we are reading the drive parameters using this BIOS function. Okay. We can delete this. Anything else that I should delete? No, I think that's it. Okay. So now, let's think about how to do that little structure that I was talking about. What I was thinking of is, because we don't have a lot of space here in the bootloader. Let's start with something simple. Okay. And I'm curious if you can do structures in... That's something that I should look into. Because those might actually be very useful. Structured data types. Okay. Okay, so the way this works is that you basically declare the structure using the res, which means reserve byte, reserve word, reserve double word, and then you can instantiate it using the I struct keyword. And then you can basically specify values for each of the fields in that structure. I was thinking of maybe doing like an array or something, but I don't know. Okay, let's just keep things simple. So, okay, let's put it at the end, right at the end. I think that's a pretty good place to put it. And I can basically change this variable to be stage 2 location. Okay, and the way this should work is let's reserve a number of bytes. Let me think. Okay, so the way I was thinking about doing this is like this. So we have like a 1 byte length and a start. The start position on hard drives, on large hard drives, it will have to be a long value, so like an 8 byte. That's a bit annoying because that's a lot of... Maybe we don't need that. Let me think about it. Okay, we probably don't need the whole 8 bytes because when we install this bootloader, we'll not put it like at the end of the disk. Although, if you have like a... So if you have a big disk which is partitioned and you install the bootloader on partition 3, for example, then yeah, these numbers might get pretty big. Okay. Yes, the code will be public. I will put it on GitHub right after I finish. Okay, so let's do something simpler this time. Let's try to do something simple here. I'll have a 4 byte, like an int LBA, and then a length. I don't know if 4 bytes is enough, but we will see. And we will basically create an array of these. Now each entry is 5 bytes. Let's think how many bytes should we reserve for this. Let's try to reserve, I don't know, maybe 30 bytes, something like that. Which means 5 bytes per entry. 30 bytes means 30 divided by 5, about 6 entries. I don't know if this is enough, but let's try to work with that. Okay, so this will be the stage 2 location times 30, and we'll just set the bytes to 0. Okay, this will generate 30 bytes filled with zeros. Okay, so now we can go here, and the next step is to load stage 2. And the way we will... Okay, so the way we will end this array is with 0 and 0. So if the LBA that we read is 0 and the length is 0, then we will just ignore it. I think that's a good idea. Okay, now there's another change that we should do here is... so we're basically, there are two sets of BIOS functions. Let me just show you that. Okay, so there are two ways of reading stuff from the disk. There is this function here, which is for reading sectors, but the problem with this one is that it's limited to 8 gigabytes, because you basically have to specify the cylinder, sector, head, and drive by using parts of these registers. And how much space you have, how many bits you have in these registers means that you cannot read anything more than 8 gigs. This is a bit of a problem, so for hard drives you will have to use another function, which is this one. Extended read sectors from drive. And I think this is something that we should also try to add to our bootloader. Okay, so let's start with this first. Okay. Now for the drive parameters, what are we reading here? So I basically used this function, read drive parameters, and this will give us the number of heads, the number of cylinders, and the number of sectors per track. But what I'm thinking about is that this is basically duplicated. We already have this information. We already have this information here in this BIOS data block, so I don't know if we actually need it. Okay, let's just delete it. We don't need this anymore. So now we saved some bytes in our stage 1, which is... The thing is that this code is... we have very little space in boot.asm. In stage 1 we have very little space, and we have to basically use as little space as we can for anything. If we can delete something, then we should. Basically, that's what I'm trying to say. Okay, so now we have to load stage 2. And the way we will do that is we will start by reading... Okay, so let's put in SI the address of stage 2 location. Okay, and then we want to load the next LBA, the next sector number. Now something I'm not sure. Okay, so I was looking at this conversion function that I have here, and it only works with 16-bit AX, and this will be a bit of a problem. We will have to make it work with 32-bit numbers as well. Okay, there's a lot of work to do, so... Okay. Let's start by loading into ESI whatever is in EAX, sorry, whatever is in SI. So the way this will work is, okay, let me just show you a bit. So let's say that this is the array, and we have 4 bytes for the LBA, and then 1 byte for the length, and then again 4 bytes for the LBA, another for the length, and we'll have this 6 times. Okay, and we are starting by reading this value here. Okay, then we can increment SI, so add SI 4, because we read 4 bytes, and then we have to read this length. We'll use CL for the length. And then we advance again. So now we are here at the second position. Okay, this will be part of the loop. Okay, so now we should have the LBA in EAX, and we should have the number of sectors to read in CL. Alright. We will have to call this conversion function, so the way this function works is... Okay, in AX it expects to have the LBA address, so let's call LBA to CHS. Okay, so the length... I think the length should be in another register. Let me check. The number of bytes to read is in CL. Alright, so I was right. Wait. Okay, so it returns these in CX. Oh, okay. So this greet function already calls LBA to CHS, so we don't have to do that. We just need to call this greet. Okay, that makes sense. Okay, so we just have to call this greet. What else do we have to set that we haven't done yet? Yes, we have to set the memory address where to store the data. That's the next thing. And the drive number should be unchanged because we haven't changed it. Okay. This is what I... Okay. This is the segment where we have to load stage 2. So let's store that in ES, and then the offset should be in... Okay, at 500. The offset is for this grid is BX. Okay, so what we have to do here is move BX stage 2 load offset. Okay, so what we're doing here is we are setting the parameters for this grid function. The AX will contain the LBA, the sector number that we want to read from. Then CL will have to contain the number of bytes to read, which is this number here. ES should contain the segment where we want to store this, and then BX should contain the offset where we want to load this, where we want to load stage 2. Okay, and that looks good. Now, after we call this grid, we have to increment okay, SI we already incremented, but we have to increment this BX. And we have to increment it by how many sectors we read. Okay, we have to multiply this by 512. Okay, so 512 is 8, 9, 10 bits to the left. So we have to shift C. Okay, we will clear whatever is in CH first, because we don't know what is in there. And then shift to the left by CX by 10 positions. And that should multiply it by 512. And then in fact, okay, I was thinking about something here. The segment, the offset is limited to 64 kilobytes, right? And what if we, instead of incrementing the offset, we increment the segment? Because 512 is basically 2 to the power of 9, or yes, 2 to the power of 9. So it is aligned to 16, which is kind of what we're interested in. So 512 divided by 16 is 32, which is which means that we can basically, instead of incrementing this offset, we can increment the segment by CX shifted to the left by 5. Is that right? I'm not sure. Let me think about this. So, for example, we have segment and offset 0, which means this address is 20,000. And we have read, I don't know, let's say we read 3 sectors, which means 3 times 512. 512 in hex is 200 multiplied by 3, which is 600 multiplied by 3. Okay, it's 900, sorry. Are you sure? Come on. 200 multiplied by 3. 600. Yes, I was correct. Okay. So what we have to do is increment this address by 600. So instead of incrementing it by 600, we can increment it by, we can basically increment the segment by 60. Because, so the segment is basically, the address. Okay, to convert from segment to an address, we just multiply by 16 or 10 in hexadecimal. Okay, so what that means is that we have to basically multiply by this number, 20 in hexadecimal, which is 32, yes. And we can multiply by 32 by shifting to the left by 5 positions. Okay, this looks good. Okay, we have done that, and now we have to add this to ES. Now, I'm not sure if this will work, but we will see. Okay. Something we haven't done here is to basically check for the exit condition from the loop. So let's do that. So if EAX is 0, actually let's just look at the length, because reading sector 0 is not valid anyway, because on sector 0 we have stage 1. So yeah, okay, it's fine either way. So if EAX is 0, we will jump to read finish. Okay, and then we will jump to loop. Okay, now let's see how we can improve this disk read function. Okay, this part looks good. So yeah, let's go to disk read. Now something we have to do here is to figure out if what kind of disk we have. And for that we have this BIOS call. We have check extensions present. So this is the first thing we have to do. And if the extensions are present, then we read using these functions here, like 42, this extended read. If they are not present, then we will use whatever we used until now. All right. Okay, so let's start by check extensions present. Okay, this is pretty simple. We have to set AH to value 42. DL to the drive index, we haven't changed it, so it should be fine. And then DSSI should point to a structure where we will basically get this disk address packet. Okay, this is the extended read. Sorry, I was looking for the check extensions present. Okay, so the function is 41. The drive index, we already have that, and BX should be 55AAH. All right. And then we call int 13h. And now we have to check whether the extensions are present. So if the extensions are present, then we will get the carry flag. It will be, oh my god, set on not present, clear if present. Okay, so we set the carry flag before calling this function, and we have to check if it has been cleared. And then BX should also have the value AA55, so the reverse of whatever we have here. Okay. So if carried, then that means it is not present. Okay, so okay, we don't have to check everything, but okay, fine. Compare BX to AA55 and jump if not equal, jump to no disk extensions. All right, and we will have no disk extensions here somewhere. Okay, so now we know that extensions are present. And what we can do here is to basically set a byte somewhere to mark if the extensions are present or not. And whenever we will go to the floppy read functions, we basically have to check, okay, are the extensions present or not? And depending on that, choose which implementation to use. All right. Okay, so and there are no disk extensions, we just set that to 0. Okay. And then we can go ahead and load stage 2. All right. So now let's try to implement these functions and see how we have to change them. Okay. We will want the LBA address to be in EAX instead of AX. The number of sectors to read is fine. Drive number is fine. Okay, so the rest is fine. Just the LBA address, we will want it to be larger. All right. Okay, so the next step here is to check whether we are using extensions or not. So let's use compare. I don't know if this will work, but I don't know, let's just try it. Okay, and this will be the implementation if we have no disk extensions. Okay, now let's see how we perform the read. AH should be equal to 42, then DL should contain the drive index, just like before, and then the segment and offset. Okay, now here's the difference. The segment and offset are stored in this structure, and this is a little structure which contains this information. So the number of sectors to read, same as before, we have at offset 2, then we have the segment and offset point. Okay, so where to store the data, and then the absolute number of the start of the sectors to be read. So essentially we are using LBA. This is very cool. We don't have to use that annoying cylinder head whatever representation. We just use the LBA directly, which is great. All right. So we need to reserve a little space for that. Extensions, DAP or whatever it's called. Okay, so this one has the size, which is byte with the value 10 in hexadecimal. Then we have an unused byte, so just set this to 0. Then we have 2 bytes, which is the number of sectors to read. Let's just call it count. And then we have the segment and offset. So I'm just gonna do the same. Segment and offset. And finally we have the LBA, which is 8 bytes. So LBA. And this is a quad, which means 8 bytes. Okay. Okay, so now we have to set all the parameters. AH to 42 in hexadecimal, but in AH we have the LBA address, so we need to store that properly. LBA. Then the segment and offset, so that is ES extensions.dap.offset. I think SI was the parameter. No, it's BX. And what else we have? The count. We have the extension dap.count. and we will set it to CL. Alright, now we've set up this structure. What is left to do is set up these registers. So AH should be 42 hexadecimal. Then DL should contain a drive index. We haven't changed it, so it should still be, it should remain. And then DSSI should point to that structure. The data segment, we've already set it here in the beginning. Here where we set up the data segments. So we just need to set SI to the address of this structure. And then we call int 13 hexadecimal. Alright. Okay, we can just go to this retry area. So jump to retry. And if we don't have these extensions, then we need to do things the way we did before. Okay. Reading the documentation, the result is the same as before, so the carry flag is set on error or cleared if there is no error. And we are setting the carry flag here, and then if there is no carry, then we go to done. If there's an error, we have to reset the drive and basically retry. Oh, and DI should contain a number of attempts, so let's add that as well. Okay, I hope I got everything right. For this reset, we use the same functions. We don't need to do any write. Yeah, there was this extended redrive parameters, which might be useful. I'm not sure. Let me think about it for a second. So here in the boot sector, we basically have the number of okay, so we have, I'm not sure. Bytes per sector. Okay, sectors per track, but this doesn't matter doesn't really matter when using LBA. It only matters when using the CHS scheme. Yeah, so these should only matter if we use CHS. Or for normal hard drives, that should really not matter. Alright, let's see if we got this right. Let's see if we can still compile this. Okay, we've got some errors at line 103, which is here. Okay, I was expecting that. You cannot modify ES like this, so we will have to do it some other way. We haven't used the DI register, so we can just put the contents of ES into DI, then add the CX to DI, and then just move it back to ES. Alright, let's see. No errors. Wow, I did not expect that. I don't expect it to be this easy. We will see if it works. I'm not sure if it will work, but yeah, that's very cool. Something I'm curious about is how much space we have left. Now that we've reduced our implementation, we've reduced how big our implementation is. Okay, so let's just use some hex viewing tool. And let's see what we've got. Nanobyte. Stage1.bin. Let's see. Okay, so we do have about... now, some of the stuff is reserved for these variables here. So, but we should have about, I don't know, let's say 64 bytes. Yeah, that's quite a lot. Actually, that's quite nice. We have plenty of space, so we can increase how much yeah, we can use 8-byte LBAs basically. I think we can use 8-byte LBAs without any issues. Okay, so now let's see how we need to change our build process to install this properly. Okay, so what we have to do first is to try to load... Okay, let's try to basically change the way... Okay, so I was saying that I want to use like a hybrid approach. Alright, so for the current image that we have here in our process, we have this floppy image. Let's try to change the script so that we can still use this floppy image. And we will test it if it works. Alright. Now, what we need to change is this make fs.fat command so that we create some reserved space. Let's see how we can do that. Okay, so we have reserved. Where are you? Okay, this is it. So -r set minimal number of reserved sectors to count. So what we need to do here is basically figure out how big the stage 2 is. Okay, how we can do that? I think stat has something. Okay, so it has stat has this total size. All right. Let's try it first. So let's take a file like, I don't know, readme. And we want to basically just show... Okay, so this is how it should look like. Okay, this will give us the size in bytes. All right. Okay, so now we know how big stage 2 is, and we basically want to figure out how many sectors is that. So the way we do that is we have to add 511 and then divide it by 512. And what this will do is basically, so let's show it in the calculator a bit. Okay, so if the stage 2 is 512, is it exactly 512 bytes, then we will add 511. Come on, 512 plus 511 gives 1023 divided by 512, which is 1.99 something, which will basically be truncated to 1. But if the stage 2 is 513 bytes, then we add 511, which gives us 1024 divided by 512, and that gives us exactly 2. So if it is 1 byte above the limit, then it will go to the next number of... Okay, that's basically how we can round this number properly. Okay, now how do we do math in Bash? That's a good question. Actually, let's see. Make math. Make file. Oh my god. Okay, so the double. Okay, I think the best option is to just use this expression. Okay, I'm not sure how this should work, but let's try it anyway. So stage 2 in number of sectors equals stage 2 size plus 511, all of that divided by 512. I have no idea if this will work, but let's try it. And to test if this works, let's just echo the value of this variable. Okay. Okay, something's not working. Yeah, this looks nasty. Okay, so Make is not very happy about creating variables. We might have to do it another way. Okay, can we do this? Nope. Okay. Make is not very happy about doing this. Double dollar sign. Okay. So there is the option of doing double dollar sign. Alright. Let's see if this ugliness of the thing works. Alright, nope, still not working. Yeah, for stuff like this, I would basically just create like a shell script and call it from make. Am I doing something wrong here? Okay, so it's not seeing that variable for some reason. Okay, let's see if this works first. Okay, so this doesn't work either. Double parentheses, or what does it want from me? Okay. Oh my god, this is annoying. Okay. Make file set variable in a recipe. I think that might be the issue, because we're trying to set this variable inside the recipe, which Make is not super happy about. Okay, it doesn't work. Yeah, I expected that to not work, because Make creates a new shell process for each of the each line basically, and even if we do this, it's not gonna work. So you know what I'm gonna do? I'm just gonna basically move this whole process of creating the image. I think I'm just gonna move the whole process in a shell script. I think that might actually be the easiest way. Yeah, that's what I was thinking. So, okay, let's just create a shell script for make floppy image dot bash. All right, I'm going to copy all of these commands, and we will need to replace everything with just build scripts, make floppy image, and let's see. Okay, let's have the target file system, the target file as a parameter. I don't think we need anything else. Yeah, that's everything I was doing here as well. Okay, so let's create a variable target, which is gonna be the first command line argument, which is basically the floppy image, and then we can replace this everywhere with target. Okay, and we can remove this @ sign. Okay, so let's see. This build directory, did I export this variable? Let me see. Yes, it is exported, so it should also appear in this file, which is great. Okay, so we have installed stage 1, and now we are trying to figure out the size of stage 2. And we can just use this shell expansion. Oh, and another thing, in shell we use a slightly different syntax for variables. Okay, so this will give us the size of this file, and then to determine how many sectors that is, let's see how we can do that. Bash math. Okay, so it's the double parentheses stuff. Okay, so we want stage 2 size plus 512, and then the plus 511 divided by 512, and then we'll print it and see if that works. Okay. And we have to do this before we create the fat file system. Okay, let's see if this script works now. Okay, make floppy image, no such file or directory. Okay, I think I forgot to add .sh, and I also have to make this file executable, so chmod +x build script make floppy image, and now we should be good. Okay, so we have 7980 bytes in stage 2 divided by 512. That gives us 15.4, and we round it up, which gives us 16. So it works. Yay! Looks pretty good. Okay, now let's clean this up. Okay, so what we're doing here is okay, generate image file determine how many reserved sectors, and then create file system. And the option was -r and the number of sectors, basically. And that should give us however many empty sectors we want. So to install stage 1, we just use dd, just like before. And then for stage 2, we don't use copy, we have to use dd as well. The input file is stage 2, the output file is target. We don't want to truncate, and we have to skip 1, and the block size is 1. Okay, so the block size is 1 byte, and we can actually use the block size 512. I think that should be fine. Okay, and we don't need this anymore. Let's make sure this works first before we... Okay, it almost works, except that for some reason we have corrupted something, which is not great. Okay, we have to debug this a bit. Okay, let's see what this command is generating first. Okay, let's reload. Actually, no, we have to open the image, main floppy.img. Okay, this is the first sector. It's all the way till... So 512 was 200. Okay, so this is sector 1, and then this is sector 2, and it looks like there's something there. So this did not work properly. Okay, let's see why. Okay, that's not that. We don't need the... Okay, so it's -r, minimal number of reserved sectors. Okay. C option A, -a. Okay, so I think this is the option, but I'm not sure why it did not work. Alright, so -r is the number of stage 2 sectors. I think we might actually need to increment this by 1, so... Because the boot sector is also among the reserved sectors. Okay. So we need 17 reserved sectors, but for some reason it's not creating those. Oh, and I know what the problem is. I think I know what the problem is. The problem is that we are overriding stage 1. We are basically overriding the boot sector, which contains the information about like how many okay, if I go to boot.asm, I'm basically overriding how many reserved sectors there are, this number here. And because I'm overriding this number with this, then whenever mcopy is trying to read the disk and trying to parse the file system, it sees that the number is wrong and it just can't make out the data. So I think that's what the problem is. Okay, so the way we can solve this is by splitting this command here. We can split this command and have stage 1. Okay, and we are gonna set the block size to 1, and we are going to write the first 3 bytes, which are these instruction here. Then we will leave whatever the formatting tool is setting, and then we will skip all the way here and write starting from this start. And we need to figure out what the address of this is. I think we have... Okay, we don't have a map. I think we can figure it out from here. Okay, so we have this fat 12. Okay, so the offset is 3e. 3e in 3. It is 62. Okay, we will double check that in just a moment, but what was the number? 62. Okay, so we skip over the first 62 bytes and then we write the rest. Now we also need to skip these bytes from stage1.bin, so let's see how we can do that. Okay, so we have to use seek for that. So we also have to seek, so we'll skip the bytes from the output file, and seek will skip them from the input file. Alright, let's double check that and see if this is correct. So os dev fat 12 or whatever. Okay, so for fat 12, yes, the boot code starts at offset 62, which is correct. The hex editor I'm using is just octeta from KDE. I don't really like hard coding these numbers, but I think we should be fine. Since we are creating a 1.44 megabyte floppy disk, which is very predictable. We know exactly what it should look like. Alright, and let's see if this works. Make. Alright, this looks good. And now let's refresh. Okay, so this section here is empty, and it's empty all the way to here, 4600. So let's try to calculate how many sectors that is and to see if it is correct. So 4600 divided by 512. Okay, that was in hexadecimal, sorry. 4600 divided by 512 is 35. And oh, okay, that was something else. That was the root directory. I found some other data here. So this is the first file allocation table. Okay, so let's look at this number here instead. 3400 divided by 512, it is 26. Did I miss another one? Oh yeah, 2200. Okay, it's 17. That's exactly the number of reserved sectors. This is where the first FAT is, and this is where the second FAT is. Because in the FAT file system you basically have two copies of the FAT. It's to make sure that if one gets corrupted, then you have a backup, you have a second one. Okay, so now we should be able to also write stage 2, and let's also send all the outputs to dev null to get rid of it. Okay, we are still having this issue. Let's see what skip does. Is it in number of blocks or is it a number of bytes? Okay, so skip will skip this number of blocks, and BS is the block size, which the default is 512. Okay, so this should write stage 2 to the second. I wonder why it's... Okay, let's see what the output of this command is. Okay, so it's writing 7468 bytes, which looks right. So why does it say that it's a non-DOS media? That is a bit odd. Okay, let's see. Let's check the boot sector that it looks good. So the number of reserved sectors is this one. So it's 512, then there's a 1, and then there's the number of reserved sectors. So let's see if we can find it. Okay, this is the OEM. Then we have 20200 because this is basically Little Indian. So we're reading from right to left, the bytes. Actually, let's group these by... Where is that option? There should be an option to group these by... Okay, I can't find it, but whatever. So, signed 16-bit, it's 512. And then we have this one, which is the number of sectors per cluster. And then we have the number of reserved sectors, which is 17. And this should be correct. So the question is, why is this not working? So we are skipping the first. Okay, let's reload and see what we got. Okay, so I think we've overwritten the boot sector for some reason. Is this based on 1? Is this indexed from 1? Or what is wrong? No. What the hell is it doing? Why is it overriding the boot sector? Okay, so we are writing from stage2.bin. We are writing into the same target, which is okay. We don't want to truncate the file, and we want the block size to be 512, and we want to skip the first block, so we want to write starting from block 1. It's doing weird things, and I don't understand why. Okay, what if I set the block size to 1 and skip 512? Okay, same thing. Alright, let's see the manual. What did I get wrong? Oh, okay. I made a mistake. So skips in from input, and seek skips from output. So I got this wrong. I should use seek, not skip. Okay, so the block size is 512. And I think the rest is correct. Here we're just writing the first 3 bytes. Here we want to both seek and skip. And here we just want to seek. Alright, and I think this should work. Okay, yay, we got it right. File system, install bootloader, and then copy files. Okay, now another thing that we haven't done here is to set up this section at the end, where we are setting this stage 2 location. And as we discussed previously, the way this will work is we have the 4-byte LBA and then a 1-byte length, and the length is also a number of sectors. Okay, and we need to write these 2 numbers to okay, let's see how we can do that. Okay, so here we determine the number of sectors that are required, but this is a bit misleading because this is not stage 2 sectors, this is the number of reserved sectors. So let's try to create a separate variable for the number of reserved sectors. Will be 1 plus stage 2 sectors. And when we create the file system, we want to use the number of reserved sectors. Okay, and now what we want to write to the file is 2 numbers. We want to write the LBA, which in our case is 1, because we are starting from sector 1 here. And we want to write the number of sectors that this stage 2 sectors. Okay, 17 and 18. This is what I was looking for to make sure it is correct. Okay, now it should be correct. 16 and 17. Good. Okay. Now let's try to figure out how to do that. So we need to, in bash, write bytes to file. Echo bytes. Okay, let's see how we can do that. Okay, we can use echo, but I kind of want to write we can use Perl or Python, but that will also add some more dependencies to our encode number to byte. Okay, let's see how we can do that. Okay, that's not helping. Oh, okay, so we can use hex dump. That's great. So what we can do is do something like just put the thing that we want to write in hex. For example, okay, 2e, and then use hex dump minus c, I think. Okay, this is not what we want. What we want to do is the opposite. So we want to convert hexadecimal into binary. Okay, that sounds like a great idea. So hex into binary bash. So there's BC and okay, XXD. This is the one I was thinking about. So let's try to figure out how to use this thing. Make a hex dump or do the reverse, and -R is to do the reverse. So this is what we're doing here, and then -P, what does that do? -P. Output in PostScript continuous hex dump style. Okay, we probably don't want that. Okay, let's try it out a bit and see how... Okay, so let's say that we want to convert XXD -R, and let's say that, I don't know, we have 2e and we want to convert that to binary, and then let's write that to, I don't know, test.bin and hex dump test.bin. Okay, that did not work as I expected. Is that what that -P does? Maybe. Okay, so yes, that's what it did. Let's see if we write something more complex, like, I don't know, 2e, 5e. Alright, now hex dump is grouping them by word. I think there's an option to not group these. Okay, so it's hex dump. Let's just use -B. Nope, that's not what I wanted. -N. Nope, that's not it. Why isn't there a... that's odd. Anyway, doesn't matter. So we got what we wanted. These are grouped in little endian, so it's 2e and then 5e and then 1 3 and then 3 7. Okay. Alright, so we can use this xxd command to basically write 1 to a file. So if we write 1, then xxd -R -P, we will get a 0 1. Okay, so it wants it to be into it wants it to look like this. All right. Now, question: can you use xxd to have like a larger integer, like a 32-bit number? That's something that I'm curious about. Oh, okay, I don't think so. So I think it's just using... Oh, okay, and you can just use it like this. You don't have to use pipes. Or maybe you do. Okay, whatever, let's use pipes, because these are fun. Okay, so to write number of LBA address of stage 2 to bootloader, and we will have to create a variable to determine where that offset is. So stage 1 how should we call it? Location offset. And we need to figure out what that offset is. So it is 510 minus 30, basically. Calculator. 510, because the last 2 bytes are this AA55 signature, minus 30, so we should be at offset 480. Okay. So let's echo 0 0 0 0 0 0 0 1 and then use xxd minus r minus p, and then dd that from to target. Don't truncate. Block size, we want it to be 1, and we want to seek by that offset that we have, stage 1, stage 2 location offset. Alright, so let's see if this works. Okay, so if we don't specify an input file, it will read from standard input, which is what we want. Alright. Now let's take a look into our hex dump. And we need to go to offset. What was that offset? 480. 480 in hex is 1E0, so it should be this byte here. Yes! Yay! It worked! Yay! I really did not expect that to work, but I'm glad it did. Alright, and now we have to do the same thing with this number of reserve stage 2 sectors for the size. Now, this is gonna be a bit more nasty. We basically have to first convert it to hex, and then use xxd to generate a file, to basically generate the binary code for it, and then same using dd we will write it to the file. Alright, so let's see how we can do that. Bash deck to bin to hex actually. So decimal to hexadecimal. Oh, really? You can use printf? Is there printf in bash? Seriously? Let's see. Printf. The format is %x because we want it to be the hexadecimal number of stage 2 sectors. Let's actually just print it and see if we get if this works. Okay, there are too many numbers here. I think it's this 10. 16, yes, 16 in hexadecimal is 10, so I think this is the one we're looking for. We really need to suppress some of the output of these commands because it's way too much. How did you redirect std error as well? I think like this. What I don't like about that is because it will suppress. No, it's not like that. It's like this. I think so. All right, so what we have to do here is just do the same, and we will write it at this location plus 4, so this plus 4. Okay, it looks a bit ugly, I admit it. I think it might be a great idea to rewrite this in Python. It might be a lot easier to do these binary stuff. Okay, let's see if we wrote the size. Octeta. Let's reload. And we have 1 here, and then we have 10 here. Yes, it works. Okay, now the moment of truth. Let's see if this ugly thing works. Okay, it doesn't work. I expected it not to work. We have to do some debugging, which is always fun. Okay. Okay, the display library doesn't like the display library. We have to do some fun debugging. So let's go to location 7C00. This is where our bootloader is going to be loaded. And continue. Now we have to disassemble again to make Bosch refresh this. Okay, so now let's look at the code side by side, because I don't like... No. Alright, let's get rid of this. Let's get rid of this. Okay, and let's do some fun debugging. Okay, so the first instruction is to jump to 7C whatever. Let's disassemble again. And now we should be right here at this start location. All right. Okay, so let's go step by step. All right, we are here at this after, so we are trying to save the DL, and then we are printing the loading message. Let's skip beyond that. Okay, now let's check if the extensions are present. So we'll call this interrupt. And if the extensions are not present, then we will jump to no disk extensions. And I expect this to happen. All right, so we don't have any extensions because on the floppy disk, this is usually disabled. This is how Box behaves. And I noticed that Chemo does the same thing. All right, so now we are here. Okay. I saw a little mistake here. I forgot to do like a jump here. All right. Maybe there's a cleaner way of doing this, but whatever. I don't want to bother. Okay, so now we should be at this move SI stage to location. All right. Which is at address 7DB5. If we look here, that should be basically here. It's essentially 7C00 plus the offset of this stuff. Did I get this wrong? Oh no, I got this wrong. Okay, here's the problem. I found the error. So I wanted to have this be like right at the end of the boot sector, but I have this times 512 minus whatever, which is basically filling everything. So instead of putting it at the end where I expected it to be, like I did not put it here, I put it like here somewhere, which is the problem. Somewhere around here. So let's change that. we will move it here after this this instruction, which is basically filling our file with padding. And we also have to subtract these 30. So subtract from 510, we also subtract 30, and we subtract the current position. And okay, so we subtract 510 minus, we do 510 minus 30 minus one of these is the current position and the other is, I don't remember. Okay, so here what we wanted to do is determine the number of padding bytes. So I think this is the size of the... I don't remember. Anyway, I'll have to look that up. Okay, let's see if this works now. Okay, we are getting something different this time. We are getting a triple fault, which is always fun. Okay, let's debug that and see what else we got wrong. Again, we go to 7C00. Continue. I forgot to put the breakpoint, damn it. Okay, we're getting that unsupported AH41. I expected that. Continue. Okay. So now we are back at the beginning. Let's disassemble again. Okay, so now we are at this start location here. Let's just go a bit down. Okay, so let's go all the way to this check extensions present, which should be after this interrupt here. Alright, we know that they are not present, so we are jumping to this location here. And here we set that byte to 0. Alright. Next we have this move SI instruction. Let's verify again that this is correct. So if we subtract 7DE0 minus 7C00, we should get 1E0, which is 480. Yes, this looks correct. Okay. Then we are setting AX to... Oh, okay, yes, this looks good. So AX is 0 because we're loading at segment 0 and offset is 500. That's the one I've set. Okay. And we have set that. And now we are trying to load the number of the LBA location of the stage 2, which should be 1. And it's not 1. Okay, what happened? Let me see in Octeta. Oh, okay, I know what the problem is. So the problem is that this is in Little Endian, so we have to start from the lower bytes. The lowest bit is the lowest byte is 1000. So we're kind of reading this like from right to left. So if we have 0, 1, 2, 3, 4, 5, 6, 7. If we see this in a binary file and we want to interpret this as a 32-bit number, we have to do 6, 7, and then this one, which is 4, 5, and then 2, 3, and then 0, 1. So this is because the Little Endian. Okay, now this should be correct. Okay, let's make and debug. Actually, let's just run it. I'm confident that I got it right this time. Yay, it works! Yay, so we got a hello from kernel. Okay, now let's try to do this with the MBR stuff that I talked about. Okay, now that's gonna be another shell script. Just like we have this make floppy image, let's create a second script. I'm just gonna copy this one. Let's name this make disk image.sh. Okay, now to create a hard drive image, let's also pass the size as a parameter here. So second one will be the size, and the size should be in what should it be in bytes. It's fine in bytes. All right. This location offset is the same, and then we want to generate a file for the actual disk, and the count should be that size again, same as we did before, size plus 511 divided by 512. So we will just round it up to the next multiple of 512. All right, so we are creating a disk image, and then again we have to determine how many. Okay, we no longer need these reserved sectors. We don't care about them anymore, but we do care about how big the stage 2 is, because we don't want it to overwrite that partition, the first partition. So we have to ensure that it doesn't overwrite the first partition. Okay, so the first step will be to create not the file system but the partition table. Okay, and let's see how we can do that. There are a couple of tools we can use. There's fdisk, there's parted, and I don't know which one is the most universal. I have no idea. Okay, let's just use fdisk. All right. Let's see if fdisk will like what we are trying to do here. Okay, so let's just create a temp folder, and let's generate an image which will be, I don't know, image.raw, and let's make it big. Let's make it, I don't know, block size 1 megabyte, and let's make it 1 kilobyte, and let's make it okay, so that should be 1 megabyte. So we have created a 1 megabyte disk. It's pretty small, but let's see. Okay, so someone is saying that there's a tool called sfdisk which allows scripting, and it is installed. Great. Okay, that sounds great. Let me try to figure out how this works. So sfdisk partition table manipulator for Linux. Okay, repartition a device. It doesn't work with GPT, and the way it works is create partition. I'm not sure if this tool can create the partition table itself. Hi, thank you for boosting my server. Frantic BO. Okay, let's see if Parted can do that. So parted. Okay, in parted we can use a script, which is great. This is exactly what we want. And let's see how we can use that script. Okay, so we just call parted and then -s so that it doesn't prompt us for any intervention, the device, and then the command. And here is the list of commands. Okay, let's see how we can create a partition table. That's the first thing we need to do. Come on, where is it? This creates a file system, this creates a partition. But how can you create? Okay, this is a partition that has a file system. I don't know. Parted, create partition table. Okay, so there's the command to set the partition table type, and I think that's the one we need. Okay. So MK label. All right, is that the command I'm looking for? MK label. Create a new disk label or partition table. Yeah, okay, so it just has a weird name. Okay. So let's see how this will work. So we call parted minus what was the argument, -s, because we want this to be a script. The device, which is image.raw, and the command is mk label, and we want to create an MBR, which would be MS-DOS. This is the one. This is what parted calls it. Okay, and let's see what we have here. Okay, so this is the program that I was talking about earlier. This is basically that little program which actually it's kind of small, I don't know, but it might be it. And it's marked as bootable, and this is the first partition. This is the information for the first partition. Yeah, I think it might be okay, because that program is pretty small. I mean, all it has to do is just relocate itself, so move itself to some other area of memory. Let's see if we can actually generate a dump. OPJ dump, disassemble. Okay, it's not recognizing the file system. Let's see if we can do okay, so okay, here we go. This is exactly what it does. Now it looks like it's using a different syntax. Let's see, obj dump help grep intel. Can we set the intel syntax? Yes, we can, but I just before 5. Okay, before 10. -m is the switch, so Intel. All right, here we go. Now this is the syntax we're used to. Okay, so it's basically, let's see what it's doing. It's setting the stack at address 10,000. Okay, so this looks like valid code. Okay, it creates a stack as we would expect. It puts, okay, so it sets the data and the extra segment to 0. Okay, and then it relocates itself. So this is what this instruction does. This reap move as byte, it relocates itself to another address. I don't know, address 600 or something like that. Okay, and then it will call in 13 hexadecimal. Now I'm not gonna go through everything here to explain how it does that, but you can look that up. AH is 2. Okay, so it's using the so it looks like it's using these simpler functions. AH equals 2 is this one. Read sectors from drive, so it uses that. And it will basically load it at address 7C00. So it that's exactly what it does. It relocates itself to some other address. This is what this part does. Then it loads the first sector of the first partition, and it basically calculates, okay, what is the position of the first partition. This is what these magic numbers are here. And then it loads that into memory, and then it jumps to 7C00. So it's exactly what we would expect it to do. This is the MBR code. Okay. So we have our first command here. Okay, I have 2bash opened. 2bash. Ah, damn it. Let me just close the other one because it's confusing me. Okay, so our first instruction is gonna be this one, which will create a partition table. Now this part is gonna get a bit more weird, because now we basically... Okay, question, do we have a partition or not? So let's see what this command did. fdisk -l, and the device is image.raw. Okay, it doesn't have any partition. So it does have a partition table. Those bytes that we've seen. Okay. I'll just open this temp file that I created. So what this is basically some metadata, which basically contains this disk identifier and the stuff we see here, basically. Okay, so now we need to create a partition. So let's do that. Let's figure first how we can do that. So parted -s image raw, and we will create a partition. And let's just create a single partition. Let's not bother with multiple partitions. Let's just have a single one for now. Okay, where is my documentation? Okay, then we have the partition type. Okay, so this will... Okay, this will be the type of partition. So let's just use like FAT16. Now, the problem here will be that our stage 2 will not work properly with FAT16 because I've only implemented the driver for FAT12. We need to make some changes to make it work with FAT16 or FAT32, but okay, so let's just use one of these. So okay, we don't have to use a file system. We can use part type is the partition type, which should be primary, logical, or extended. Okay, so this will be a primary partition, obviously. Primary, then the file system. We don't have to provide that, only if we want to. And then we have to specify the start and the end. Okay, now let's see what start we should provide. Let's see what happens if we don't provide anything. Okay, if we don't provide anything, then we get nothing. Okay, so I think this just returned an error without telling us about it. If I remove, okay, it's asking us for the file system type, the start address, and then the end. Okay. So, the start and end. Okay, how are these specified? Let's see. Start is start like a so what is start? I think okay, so start is by default in megabytes. Okay. Okay, so start is in megabytes, and then end I don't really like about this because you cannot specify to use like 100% of the disk. We have to figure out how to specify these start and end. Okay, so let's create a primary partition, and the start should be at so the start should be at 63 sectors. But how can we specify that? So that would be 32 megabytes. 32. Hold on a second. I think this will not work. I have to create a bigger image. Okay, so a 1 megabyte image is not gonna work for this. I'm confused. It's okay. 1 megabyte is enough. 63 sectors means 32 kilobytes, not megabytes. Okay, so basically what we have to do is make a partition of type primary, starting at 32 kilobytes and ending at 1 megabyte. Okay, so it's not properly aligned for best performance. And why is that? It is expecting it to be aligned to 2048. So you can see that the default tools will actually reserve even more than 62 sectors. Okay, so we can set it to 2048 sectors, but I think that okay, and the total image size is, I don't know, let's just say, now that's the problem, the image is kind of small, so let's create a bigger image. Actually, let's just not bother with this anymore, let's just go straight to the code. Okay, so we created this disk. We kind of need this number, so let's save it. Disk sector count. Alright, and instead of using this, we will just use the disk sector count. Okay, and then we will create a partition, and it will start at, it will be a primary partition, and it will start at, so let's just use the number that, 2048 sectors, and it will end at disk sector count sectors, like this. Okay, now let's try to test this and see if it works. Yeah, these will fail. These will definitely not work. I'm just gonna comment them. Okay, and now in our main make file, let's create a different target for the disk image. Alright, and we will have this main disk.row, which will be created by calling the make disk image script. And let's just use this config file from make to specify how big this should be. Make disk size, and let's just use a big number here, like okay, let's create like, I don't know, 16 megabytes or something like that, or 16 megabytes is fine. 1024 multiplied by 1024, it's this big number here. Okay, 16 megabytes. And then here, when we call this, we will also include the disk size. All right. And now let's call make disk image. Okay. Line 9, we have some errors there. Let's see. At line 9. Okay, I'm missing a parenthesis here. Okay, so we have generated this. Okay, so the problem is that I have to use the target variable for the file. Okay. The location 32, but that's not correct. 32,768. Do we need to subtract 1 maybe from the disk sector count? Okay, let's just do disk sector end. Let's just call it the disk sector end, which will be disk sector count minus 1. Okay, and now we have a partition. Let's inspect this with fdisk -l build main disk.row. Okay, and we have a device which starts at 2048 and it ends at sector 32,000 whatever, 16 megabytes, and it doesn't have any file system. Okay, that's great. That's really great. Okay, now for the next part, this is not going to be very pleasant. Unfortunately, I don't know of. So this is kind of what we did with mtools. Mtools are basically a suite of tools which can manipulate FAT file systems directly without having to mount them. And unfortunately, I don't think there's any way of doing that with disks. So we have to mount the disk basically. Okay. Mount disk image. Raw disk image. Let's see how we can do that. Now, okay, so this one is not gonna work. This is how you mount a partition, not a disk. Now, this is an actual disk. Loop disk. Okay, so it's a loop disk basically. It's a loop device. That's what we have to do. And unfortunately, to do this, we will have to we will need administrator rights. We will need to use sudo when we generate this image. This is unfortunate, but I don't think we have another choice. Okay, that's not gonna be a good idea. Anyway, so we basically have to use this low setup command to basically attach the disk. I think in macOS this is called HD attach, and in BSD based operating systems it's also probably the same. Okay, okay, so let's see how we can do this. I'm gonna try it here first, and then we will see if this works. So, low setup. The name will be, I don't know, let's say nano NBOS, and the back file will be build main disk.raw, and let's mount it at a loop device, but I think loop 0 is occupied on my system. Let's try to find an empty one. So f disk minus L. Okay, there's a lot of loop devices, and this is something, if you use Ubuntu, then the snap system from Ubuntu will create a lot of loop devices, and we just need to find an empty one. I don't know, loop 99 for example. It's not used anywhere, so let's just use let's try to use loop 99. I wonder if we can actually name these. Okay, no such device, but what if I do loop 99? Okay, let's see if we can actually create one of these loop devices. Okay, so this is how we have to do it. Low setup minus FP. Let's see what these mean. So minus F is find the first unused loop device, and it will print its name, basically. Okay, and then P means, let's see, minus P is to force the kernel to scan the partition table, and this is something that we have to do because we have partitions here. All right. And the image is build main disk.raw. Okay, permission denied, so just call sudo. And now if we run fdisk minus L, okay, I don't know which one it is. Great. I think this is the one, loop 3. But yeah, we want to know which one it is. Okay, question, how do we destroy a device? Let's see how we can do that. Okay, so it's minus D and then the loop device. Okay, we have to be careful here so we don't destroy anything we shouldn't. And I think the device it used is loop 3. If I look here at this list, loop 3 has, where is it? Loop 3 has exactly one partition which has 15 megabytes. This is the one we created. Alright, so now we have destroyed that device, and now we should not see this loop 3 here anymore. Loop, okay, loop 2 and then loop 4, so we destroyed it. Okay, now let's see if we can also have okay, it's not working. So how can I get it? Okay, so this command will show me what the last partition or the last loopback device is. Okay, let's see. The problem with fuse ext2 is I don't know if that's gonna work, because you basically need to do the file system. You have to basically load the partition table, and then you have to mount that partition. So I don't know if fuse will work for this. It's nasty, I know, but let's see if this works. So low setup minus a. All right, this is not helpful. Okay, but at least we can filter the output of this command. So grep, we know that our image is called main disk.raw, and we can find it this way. Okay, I'm a bit uncomfortable with this, but I don't think we have a better option. And then we destroy the loop 3 device using -d. Okay, so this is what we have to do. Okay. Attach a loopback device or create. Okay. Does low setup have like a okay, so there is a show command. Let's see if that works. If we can just use ---- show. Yay, okay, that's great. So we can use the show command. All right, so we will just call lo setup, and let's save this. So device equals the output of this command, and for the disk image we have target, the target variable. Okay, and finally we want to destroy this. So destroy loopback device lo setup minus d. Okay, it's lowercase d, and the loopback device is $sign device. Okay, so now we know what the device is, and we want to basically okay, so now that we know that the device is dev loop 3, let's determine the partition name. Okay, not like that. -l, and I don't think we need sudo. Okay, we do need sudo. Okay, so the partition name is dev loop 3 p1. I don't know if there's any point in trying to parse it, because we know it's gonna be the first partition. Okay. So let's just say target partition is device followed by p1. Okay, and now we can create the FAT file system. Let's just use FAT32. Let's not bother with any smaller FAT anymore. We don't need the reserved sectors anymore. We can keep the label, and the target is target partition instead of target. Okay, so that should create the file system, and then we have to install the bootloader onto this partition. So we just do whatever we did here. Okay, install the bootloader to target partition, not target. Okay. But there's gonna be a little problem here. This will not work. We still need to create the stage 1. Okay, so we want to install stage 1 onto the partition. Let's do that. And then we want to install stage 2 on the disk itself, in the space between partitions. Okay, so in that case, we have to destroy this loopback device. Actually, can we do this earlier? I think we can do this earlier. So we don't have to... Because otherwise we would have to create that loopback device again to copy the files. So let's not do that. We generate the image file, we create the partition table and the partition. And now we write this stage 2. Okay, let's see, let's determine the size and then the size in sectors. And then we want to make a check, basically. Okay. So let's say partition disk part 1 offset, and let's set that to 2048. Okay, sector begin. Okay, and then we want, okay, let's just clean up this a bit, and let's call this also partition 1, and we want it to be at sector count -1. Okay, this looks a bit cleaner. And then we create with begin and end. Okay, so we have created the partition. Now we are writing stage 2 to the space between partitions. Okay, so we determined how big stage 2 is, and we want to make sure that it is smaller than this number here. So if stage 2 sectors, and we will subtract the boot sector from this, because we are writing it at sector 1, and we want to determine whether it is smaller. Okay, let's see how the syntax for this is first. Okay, so we just have to escape this character. So if the number of stage 2 sectors is larger, okay, so if it is larger than where this begins, larger than or equal. Let me see then. So if the number of sectors -1, no, the number of sectors is larger than where this partition begins. Okay, so that means that if the number of sectors is 2048, then it will be equal to this, and it's fine. Okay, so greater than this -1. Because we are also subtracting the boot sector, that MBR sector. Okay, then we want to throw an error, so exit 2 or something like that, and let's just print an error message like too big. Okay, and if everything is working correctly, then we want to write stage2.bin to the target file, starting at sector 1, from the second sector, or sector 1. Okay, that looks good. Okay, and then we create the loopback device. We create the file system onto that partition that we created earlier. We install the stage 1 bootloader into that partition. Then we write the LB address of stage 2 to the bootloader, which is also 1 because it's at sector 1. Okay, and then the number of sectors is also stage 2 sectors, so this looks good. And then we just copy some files to the disk. And this looks great. Okay. There was one more thing that I wanted to check. If when I create this partition, let's see if it is active. That's what I want to see. So, okay, we want to set it active. That's gonna be... Okay, there's this boot flag. It's not called active, it's called boot. In the world of parted. Okay, so we basically use set, then the partition. Okay, so let's do that. Parted minus s target set partition is 0, I think, or 1. Let's try it and see if it works. Then the flag boot, and then the state, which is on. Okay, let's see if this works. Okay, moment of truth. Let's do make okay, make this image. Okay, so partition doesn't exist. Okay, so maybe it's partition 1. Part set 1 boot on. Okay. Let's see. Invalid option 1. Okay, let's look at an example of parted. Okay, let's see an example. Set 1 boot on. It looks good. Set 1 boot on. That's exactly what I did. Okay, so maybe this failed. And we need to see why. It might be a good idea to use that bash option, which exits the script automatically when it fails. Okay, set -e. So we know if something fails. Okay, so this parted call failed. Invalid option 1. Let's check the syntax again. Okay. So parted -s target set 1 boot on. I don't see anything wrong here. Parted target is build image dot main disk dot raw set 1 boot on. You are not a super user. Partition doesn't exist. Why doesn't the partition exist? That's a good question. Okay, parted. Okay, let's see how we can print the partitions. Okay, -L. and then build main disk.raw. Okay. What about sudo? Nope, that's not what I wanted. -L. Okay, that. Oh, okay. So the problem was that -L lists partition layout on all block devices, and that was the problem. So that's not the command I'm looking for. I'm just looking for print. So parted -S print. Okay, so why do we not have any partition? That's odd. Because this should create the partition. Okay, let's just delete this file first. Build main disk.raw and run make. Make with disk image. Okay. So we are generating this file. Okay, nothing. Let's test this command then. I'm just gonna echo it so I can copy and paste. Okay. Okay, so it created. So where is this coming from? Invalid option 1, because it doesn't execute this. Okay, let's just echo all of these commands. Before executing. Okay, so it does create the file system. Oh, okay, so that's the problem. This should not be -1. Okay, found it. Part 1 end is disk 1 sector count, which I calculated it. Okay, that should fix it. Alright. Now we're talking, and now it cannot find an unusual device because we don't have admin access. Okay, so let's run this with sudo. Okay, this is scary because if we get this wrong, then we might overwrite some disk or something. So it's very important to get this right. Okay, I can delete these echoes here. It might be a good idea to add some logs here, to add some prints. Okay, let's see what happens. So, could not get the geometry of device, error reading FAT. Okay, and I think the problem is that we are forcing FAT32, but the disk is too small to use FAT32. Okay, that was one problem. Let's see what else. What other problems there are. Alright, so we are creating okay, we have created some loop devices here. Yeah, this is a bit of a problem with using disk set -E, because now if there's an error, then that loopback device will not be destroyed. Okay, let's add some print messages because these might actually be very useful. Okay, so echo generating disk image. Okay, then we will say that we are generating partition table, creating partition. Okay, now for the tricky bit. Echo create a loopback device, and then okay, formatting. Actually, just I think we can delete this. So formatting, and then installing Bootloader. Okay. Okay, we still have a lot of these useless logs, but okay, so formatting this, installing the bootloader. Okay, and then could not get geometry. So the problem here is in our stage 1, because we basically have to reserve some more space for the FAT16 and FAT32 file systems. Okay, so let's go to OS dev in the FAT article, and let's see what else we need to create. So for FAT16, okay, for FAT12 and FAT16, the boot code begins at address 62, but for FAT32, that begins at address 90. What we could do is just have it be at address 90 regardless of what type of FAT it is. I think we can spare, let's see if we have enough bytes for that. So what we can do is just repeat this instruction to add some padding. And we know we have to begin at sector 90, so let's just do that. Okay, and it still cannot get the geometry. Okay, the geometry issue is because of this 90, and just use 90 for everything. All right. Okay, almost there. Could not get the geometry of device. Yeah, somebody's asking how complicated Limin is, and I'm not really sure because I have never used it. Let's actually take a look. Is it laminin? Limin. All right. So okay. So it does look like it's fairly complicated. It supports quite a lot of file systems. Let's see if they mention how it works anywhere around here. MBR. Okay, so it does have laminin deploy, which is basically a script which does what I did in that shell script. Okay, it doesn't say here, so I would have to dig through the code, which I'm not gonna do right now. Okay. So, what is wrong here? What is the problem? Okay, I changed things in make floppy image instead of make disk image. That was the problem. Happens sometimes. Okay. And it still cannot get the geometry of the device. Alright. But if we don't install the bootloader, let's see if, and this stuff, okay, it still cannot get the geometry of the device. So this means that it's a problem with the M tools themselves. It's not a problem with the way I'm doing this. I'm installing the bootloader. It's a problem with M tools itself. And I think I've seen this error before and I've encountered it. And the solution was to simply use M format instead of MKFS FAT. I think that might be the easiest option. M format. Let's see how this looks like. Okay, so M format for the label, I think it's -L. If I remember correctly, no, that's the fat length. Okay, it's -V for the label, and then we just create that target partition. Okay, so let's see if that solves the issue. Okay, so missed something. M format, and then the target partition. What did I miss? Is there any required parameter that I missed? Okay, and tools version, usage. Pum pum pum. Okay, let's echo this command. Did I get something wrong in the script? Does it not like the label? Let's try it. Okay, let's try it without the label. Nope, it's not the label. All right. Maybe it expects me to provide this fat length, but I don't see any other required parameter, which is odd. The string from the label. I did try it. I just left it like this and it did not work. Still getting the same error. Okay, let's go to the manual of M format. Okay. Okay, so -V specifies the label. Does it require me to set like cluster size and that kind of stuff? Is there any example? Nope. Okay, no clue. Okay, we're leaving makeFS.fat. I think this works better, but I don't know why this is. Okay, let's see copy. Okay, since we are using the, basically doing the, since we need sudo access anyway, we might as well just mount it, so that might be easier. So let's just create a temporary directory. I don't know, let's just say nbos, and then mount the target partition to this temporary location, and then instead of copy we can just use the normal copy utilities like cp. Okay, then make a directory. test, and then we just copy this file into that test directory. So cp test.txt to temp nbos test. Okay, and then let's just unmount it. Unmount temp nbos. Okay, and we can just add a message here, copying files to. Okay, so now we have the bootloader installed, we have the files copied, so we have everything that we want. This loopback device should be destroyed. So in theory, we should have a valid image. Okay, so now let's do fdisk -l build main disk.raw. Okay, so it looks like it has the Linux type. I don't know if that's gonna be a problem. I don't think the fat file system cares about that. Okay. Okay, let's run low setup and then mount it manually. So dev loop 37 to temp wrong file system type. Okay, it's partition 1. Yes, and let's see the contents of temp. Very clever name. All right, and there it is. And now let's unmount it. Okay, and if we run lsblk, okay, we have this partition. Okay, so fdisk -l dev loop 30, what was it? 37. Okay, it still says Linux. I'm not sure if how can I show the file system? Okay, so the mount command should show it actually. Alright, so let's just mount it back. P1 and mount. Okay, and the type is vfat, which looks good. Which looks like it works. Okay. Okay, let's unmount and just get rid of that temporary directory. And let's also get rid of that device 37, I think it was. All right. Okay, so now we have an image. Now we have a valid image. Now let's see if we can boot it. Now let's create a copy of this run script, run.sh. And let's call this run disk. And instead of fda, we will just call it hda. And main disk.raw. And let's see if this works. Run disk. Okay, read from disk failed. Booting from hard disk. Okay, this loading message is from our stage 1. And I think this is the message from stage 2. Let's check. Read from disk failed. Okay, so this is still from stage 1, which is not great, which means that we have a problem with how we okay, so let's try to debug this and see what has gone wrong. Okay, we will also need a box config for the disk, for let's call this box config disk, and I'm gonna move it. Okay, we don't care about floppy A. Let's see how we can create a disk. Options, configuration options. No, not that one. Not the compilation. The configuration file, yes. Disk. Okay, so we have ATA, one option. There might be other drivers. Okay, that's for USB stuff. Yeah, I think it's that ATA option. Alright, here it is. Here's an example. Okay, so ATA0 master will be a disk, which the path is build main disk.raw. I don't care about this stuff. Let's hope it can figure it out, because if it cannot, then it will not be pleasant. And then we want to boot from the disk, and we don't care about the floppy anymore. Okay, and now let's duplicate this debug.sh file. Debug disk, and we will just run using the other configuration file. All right, let's see if this works. Okay, so we have something. Let's go to address 7C00. Okay, now first we will see here is that code from the boot sector. It's that code from the MBR, so we need to continue again. And let's decompile again, and this should be our code for the boot sector, and it doesn't look... What the hell is this? Okay, so something has gone wrong. I'm not sure what. Okay, so let's start over. Reset. Continue. What is going on? Why is this all zeros? Something has gone wrong with loading that boot sector. Alright. But somehow it still ends up in that boot code. But not when I do debugging, which is weird. Okay, so I think I know what the problem is. Because I've seen this before. Okay, let's just go through and debug this a bit and see what is happening. So we are setting up the stack, which is something we expect. Then we are relocating the kernel to that address, and then we are jumping to that address. All right, and now we need to go to address 621. Okay, does this look right to you? Alright, so now it comes here. Let's take another look at that object that we created earlier. Okay. And we can just use the main disk. And let's output this to boot.txt or something, so we can take a look at the code. All right. Okay, and now let's run the debugging. Okay, cannot open hard drive image. Sudo make disk image. Okay, so for this error we can just use -p when we do that directory. So make a directory -p. Alright, now we should have the image. And it cannot open the hard drive image file build main disk.raw. Why could that be? Image locked. Do we have something that's using the disk image? Oh my god. Okay, we have to destroy all of these. Loop 3, loop 4, not loop 5. Okay, so let's just do grep main disk. And we have 1, 2, 3, 4, 5, 6 devices that we need to destroy. Can we specify them all at once? Sudo. Okay. It still cannot open the hard drive image. Why is that? Because it has a .log file, that's why. So we just have to remove that. Build main disk.show.log. Because yeah, so the problem is that I exited from box using Control-C. That's why it did not like that. Okay. So yeah, it's not working. Let's try to debug it. I will reset. Let's go to address 7C00 and reset. Okay. We need to do this again. And let's see what this thing is doing. So, okay, we are moving that bootloader to this address, and then we are jumping to this address. All right. Okay, so then we have this move si7be. Okay, let's get to this int 13 hexadecimal. Continue. And theoretically this should load the first sector. And let's see what we got. Okay, so I'm gonna look at the documentation for this in 13 hexadecimal. Let's see what this function is supposed to return, so we can check. Okay, so AL is the actor sector's red, AL is 1, AH is the return code, which should be 0, I think. And then the carry flag should be cleared. Now I don't know which is the carry flag, so the carry flag is the first bit, so it doesn't end with a 3, for example, so it's the first bit is 1, the first bit is 0, the lowest bit is 0, so then this operation succeeded. Okay, and then this jumps to 7C00. And why is it empty? This makes absolutely no sense. I don't really know why our quality is maxed at 480p. Yeah, that's odd. Anyway, Box is doing something weird. So maybe it's not reading from the correct sector or something, because this is weird. I mean, in if I run it with Camel, it is loading stage 1, but it's failing to load stage 2 for some reason. It's failing to read from disk. But in Box, it's not even reading stage 1, which is odd. Okay, so it's trying to boot from hard drive. It's running that code, that MBR code, but for some reason it's not working properly. Which is odd. I don't know. Could it be the disk or something that it doesn't like? I'm trying to find here. Okay, so it's using some auto detect geometry thing. Yeah, I do have this configuration file for Box, which is why I think this is odd. I'm trying to set the disk here, but for some reason it doesn't like it. It doesn't work. Okay. Let's see if there are any other ideas. Okay, so there's this mode, which I think it's flat. I think this is fine for me because this is just a raw image in LBA order. Is it loading it flat? Okay, let's see. Is it loading it flat? Hard drive, flat mode. Okay, so it is loading it correctly. Cylinders, heads, and sectors per track. I think I don't care about those, but yeah, it could be those that are wrong. Okay, so it's using this geometry. 32 heads, 16 no, 32 cylinders, 16 heads, and 63 sectors. Okay. Type disk. Yeah, I was thinking about the same thing. Maybe I need to I do have type disk. Maybe I need to specify the cylinders and stuff. I'm not really sure. But maybe it could be an issue with the parted MBR itself. Okay, let's fix that issue. I saw there was an issue if I use fdisk on the build main disk.rom. Okay, so it does say that the type is Linux, which is probably wrong. I'm wondering if it's something about that. Although in QEMU it works and in Box it doesn't, so I don't know what to say. It could be just Box being weird because it's not the first time I've seen this. Box does a lot of weird things, and compatibility issue. Okay, let me check. No, that's just a floating point unit or something. So the thing is, it's booting from this address, it's trying to relocate and reload, but for some reason it's failing to load the file. It's just all zeros. So what I'm thinking is that maybe it's yeah, it might be this. It might be this CHS translation thing. Okay, so I wonder if we set that to manual, or I don't know. Let's see. Okay, let's see. Okay, so translation none. What is that? Okay, so should we set this to auto maybe? But I'm not sure if that is the problem. Okay, so we probably need to I'm not really sure. Okay, here's another odd thing. In this no, it's not MKFS path. It's the MBR, the master boot record. It's generated by departed command, and I think that might be wrong. But I think the issue might be with how Box converts from this CHS from LBA to CHS or something like that. Now I wanted to see how if this boot code, if it actually makes any assumptions about that, because I think it might do assumptions about the geometry of the disk. Okay, so let's try to use parted again. The disk image is build main disk, and let's do a print, and let's see what this reports. Okay, nothing about okay, I'll have to search a bit how this MBR works, because I think that's where the problem lies. Geometry. This doesn't even care about the geometry, but for some reason it makes assumptions in this because here's something that I noticed. In this code, int 13 hexadecimal is only called once, with AH2, so it's not even reading in like LBA mode. It's reading in CHS mode, cylinder head sector. So it's making some assumption about the geometry, which I think is the problem. Okay, it does some jump here to 49. Okay, that's the end. Okay, so that's probably from the partition table. Okay. I don't know what it's doing. It's making assumptions about the number of heads and sectors. Let me think a bit and try to figure out what it does here. Okay, so 7BE, that's probably... Okay, so it's looping over the partitions here. That's kind of what it's doing. Yeah, it's definitely parted making assumptions about the number of sectors and heads and that kind of stuff. Okay, CHS mode. Linux usually detects the BIOS geometry automatically, however sometimes it gets it wrong. Okay. Okay, so we've seen the error. Okay, I think I have an idea. So let me just modify something here to show you. So the first partition is beginning at 2048. Let's try to change that number a bit and see what error appears. Okay, so let's make the disk image, and then it says this: the resulting partition is not properly aligned for best performance. So I think what it's trying to do is, so I think it's expecting it to be aligned to 2048. 2048. So how much is that? So if we assume that it has this number of sectors, which is 64, then 2048 divided by 64 is 32. Okay, so it's assuming that it has 32 and 63. I think that's the assumption here. And then the number of heads, this is basically how the image is. Okay, so I think that's what we have to do. If we look here into what Box is reporting, it's saying that, okay, it's using 163063. It's not using 3263, it's using 1663, which I think is the problem. Okay, so in that case, let's fix this. Okay, so what we can do to fix this is to go in the box configuration, and here we just need to specify the cylinders, heads and sectors. So cylinders, Okay, SPT is 63. And heads, no. Yes, heads is 32. Okay, now let's see if okay, let's fix that issue we have from let's change. Okay, and now let's remake the image and go into debug. Could not open image. Okay, so I think it's also expecting to get what? Yo, what's going on here? Oh, come on. Come on. What? Numerical parameters. Heads was set to 32, which is out of range 0 to 16. I think we have the problem. Because Audit makes this assumption, so that it's using 32 heads, so 512 cylinders, 32 heads and 63 sectors per track. But Box is saying that the number of heads is too large. Okay, question. Can we change the geometry used by parted? Okay, let's see. Yeah, unfortunately I don't see anything. 4.5 hours, wow, yeah, that's a long time. Yeah, I think we might have to end this soon. I really want to get this working, though. Okay, if you don't mind, is it okay if I take a little break? I need to do something. I'll get back to you in a few moments. Okay, so let's take a 5-minute break. Alright, so I will do a 5-minute break. 5 minutes, that looks good. Wait, how can I change this? Okay, we are gonna take a little break here. I will be right back and I will try to fix this issue, basically, when I get back, okay? Okay, see you in a few minutes. Okay, I'm back. Yeah, you can hear me, right? Okay. Yeah, so I think the problem is with parted. Parted makes this assumption that we have this particular geometry. And the way the MBR code works is using this assumption that we have 32 heads. And when we load this image into Box makes a different assumption. Box assumes that the image is 16, it has only 16 heads. So, I don't know, how can we solve that? Yeah, let's try to figure this out. Building box from scratch? Yeah, that's not... that would take too long. But for some reason, for some strange reason, we cannot set the number of heads to 32, which is... I don't know, why is that? Is it something because of... Okay, so let's try to think about this. Let's see how this int 13 works. Okay, so let's go to read sectors from drive, and so the head is 16. The head is an 8-byte value. So in theory, it should work. Okay, the problem is the number of sectors, which the number of cylinders, which is a maximum of 1023. The sector number is 6 bits, so it's from 1 to 63, and the head number is an 8-bit value, which should be 0 to 255 theoretically. So I don't know. Discord can help. Discord. Let's see what people are saying on Discord. Maybe they can help. Any ideas, guys? Because for some reason this is not working properly. The code on the live stream is super messy. Yeah, I know. I know. Alright. Okay, I don't see any suggestions here, but yeah, maybe. Box had a lot of issues recently for me, and I'm not very happy about it. Okay, let's see for head. Not here. So heads only valid for disks. Does it say anywhere that it has to be under 16? Heads. That is weird. That is strange. I'm not seeing any suggestions about it. Okay, yeah, we should try camo, I agree. Box is just making my life a nightmare right now. So let's do camo. Okay, let's see how we can debug with camo. I think I'm not sure if I've done this before. Okay, so we have the -s option. and minus GDB, and we have to choose an option like serial socket or something like that. Okay. And then we run GDB, we attach basically to this port. Okay, let's do that. I'm not trying to debug box anymore because it's just too much pain. All right, and okay, so I'm just gonna use this command, and let's see what else we have to specify. So minus s and then minus GDB. You can debug through stdio, really? Wow, okay. We'll figure it out, don't worry, we'll figure it out. Okay, so okay, I understand what it's doing here. So basically they are creating a script which has this stuff inside. Okay, let's just use this because I like this. So I have to create a script dot debug script dot gdb, and I don't have any symbols right now, so let's just add this command. This is fine. Okay, so the disk image is gonna be this one. Okay, and let's see if we can debug with GDB. GDB minus x debug script. What? Okay, it's fine. So GDB minus x debug script dot GDB. Okay, connection reset by peer. What is the error? Chemo command not found. Alright, so we have to use chemo x86 or something like that. Or i386, yeah. Okay, and here we go. And okay, we have to put a breakpoint. Okay, so let's break at 7000. No, break at the address 7000. No, it's not like that. Okay, let's see how we can do that. Add address. Okay, so it's a star. Yeah, we have to put a star there. Okay, and then now let's continue. Okay, so now it should run that MBR code, and now it should run that our own bootloader. Let's see if we can use that TY that GDB had. I don't remember what the command was. Control X, Control A. No source available. Okay. Can we show like this assembly? Keys maybe? Okay, I don't know how to do that. Show, okay, GDB show this assembly. Okay, layout ASM. Okay, nice, yes, this is great. This looks great. Okay, so there is some code there, but I don't recognize it, which is odd. Okay, no, it's fine, it's fine. So let's go. And cannot find bounds of current function. no, GDB keys. Next instruction is N. Why isn't N working? Next assembly instruction. Okay, so we have to use step I or SI. Yes. Okay, so now we are at 7C5A. Okay, let's go into our code and try to figure out what is happening. Okay, and let's put this like here so we can see both. Okay, putting something in EAX, whatever is at this address. Okay, and I think something looks odd here. What's up with that D88E? Okay, it's segment 0 and then offset D88E. So I think that is that looks good. Let's go to the next instruction. Okay, so now we are setting up our okay, we are setting up our stack. Okay, then we are pushing. Okay, we have this return F. Okay, and now we are here. It's a bit confusing because I'm not used to this AT&T syntax. I'm usually used to the Intel syntax. That's what I've always used. Okay, so now we are setting up for... Okay, we are printing that message. Okay, let's see how we can... NI to step over call instructions. That's what I want. So NI. Next instruction. So we are at... No, it hasn't jumped over. How can I step out of assembly? Step out assembly. Does finish work? Nope. Step out. Okay. Okay. What is this? Something went wrong. I don't know what. Let's try again. Okay, so break at 7C00 and let's just run. And again. And now our layout ASM. Okay. Next instruction. Okay, and then we have this call. But okay, so it's just this call here to put S. So next instruction did not work. Let's try step instruction. Okay, this one did not work either. Fin, okay. Looks like we just have to run this manually. Okay, there's the problem. What is going on? So it's input S. Oh, I know. I think it might be that interrupt call. And it's not jumping over the interrupt call, which is annoying. Okay, I think we can improve the script by adding break at 7C00. and layout ASM, so we don't have to type this every time. Is there a problem? Okay, so let's continue and break one more time. Okay, so this should be in our code. Okay, let's go with the next instruction, and when I see that call, I'm just gonna create another breakpoint because that's probably okay. So let's break at 7C77. Actually, yeah, okay, 7C. Break at 7C77, and of course star asterisk. Okay, and continue. Yay, that's the spirit. Okay, next instruction. Okay, we enable carry and then we call int 13 hexadecimal. I don't want to go into that interrupt, so I'm just gonna create another breakpoint at, I don't know if I don't want to restart debugging again, so let's go to 7D and continue. Okay, so now we should be at this jump with carry. We are checking if there are those disk extensions, if they exist. So let's see, do they exist? Okay, so this carry flag check passed, which means that we do have disk extensions. And now we also verified. Okay, and that BX is also AA55. It has the value AA55, which means that we're okay, we have extensions. So we are going to set this byte to 1. I'm not really sure why GDB is showing me this. Okay, let's move on. And now we have this jump to after disk extensions check. So okay, so now we should be here at this step. Okay, we are loading the stage 2 location pointer. We are loading the stage 2 load segment and in AS, and then the offsetting BX. That looks good. Okay. Next we have this. What is this? Okay, we are increasing SI by 4 and then increasing SI by 1. And now we have reached this jump E. Hold on. Okay, so we are comparing AX to determine whether we are finished. Okay. At this point, we need the registers, so let's see how we can get them. Keys, registers. Anywhere around here. Do we have any registers? Okay. Display the general registers. TUI reg general. Reg general. Okay, now we have registers. Okay, so EAX is 1. It's not 0, so this means that we are calling this discrete function. And we want to read 16 sectors starting at sector 1. So far so good. Okay. And now we are calling that discrete function. So let's go into discrete. Alright, here we go. We are pushing these registers to the stack. We are checking whether we have extensions, and if we don't have extensions, so if it's not equal, then we jump Okay, we do have extensions, which means that this should be okay. Okay. Then we set... now in this syntax, it's basically in reverse. So if in the Intel syntax we copy from right to left, here we copy from left to right. So we are copying from AX into this, whatever this is, address. I wonder what the segment registers look like. Is there a problem with those? Or why does this say 68C? Because 7DCB looks correct, but what about this stuff? And that's kind of what I'm wondering about. Okay, anyway, let's just go on. Okay, so AX contains 1 and we are copying it to that LBA location. Then we are copying the segment from ES to that segment. We are copying BX. Okay. And then we are copying from CL into the count. Okay, so I think we could use, yeah, it's fine, it's okay, it looks good. All right, then we set AH to 42 hexadecimal, we set the pointer to 7DC3 in ESI, yes, and we set EDI to 3, which looks good, and then we jump to the retry label. Okay. All right, here we are pushing some stuff to the stack. We are setting the carry, and then we are calling interrupt 13. Okay. Let's put a breakpoint at this line here. Hold on. Yes, at this instruction here. So break at 7D52. And continue. All right. Okay, let's see what is this supposed to return, and we can check then against. So int 42 return. In AH there should be the return code. Which in our case is 0 because AX is 1, okay, and then the carry flag should be set on error. Let's see how we can show the carry flag. Print status of carry flag, info registers, E flags. Info registers, flags. Okay, we don't have carry flag, which means that carry flag was cleared if no error. Alright, so this means that the operation succeeded. Okay, next instruction. Now we are cleaning everything up. Okay, so we are in this pop 8 right now. We are popping things, and then we are returning here to over here. So now we are here. Okay, maybe this calculation is wrong. I don't know. Let's see. Okay, so now in CL we have the number of sectors, and we are trying to figure out how wait, what was I doing here? Okay, so I was incrementing the extra segment. That's what I was doing. I remember now. Okay, so we've read 16 sectors, which is equal to 8 kilobytes. Let's see. Okay, 16 times 5, 12 in 16 times 5, 12 is that number, which in hexadecimal is 2000, which means that we have to increase the segment, so the ES register, by 200. So let's see, info rec I think there should be info registers segment, probably. Okay, info register seg, info register segment. Okay, let's just show all of them. I missed it. Info reg. Okay, so ES is right now set to 0. Okay, so after this operation, it should be 200. Let's see if this worked. All right, so we are shifting EDI by 5 positions, and then is this? What am I doing here? Okay, so I shifted this to the left by 5 positions. Okay, then I'm copying ES into DI. So I'm copying from... Okay, now I'm adding these 200. So ECX should be 200. It is 200. Okay, so we are adding 200 to EDI. And now we are copying that back into ES. Okay, so now if we info reg ES is 200. Okay, this looks good. Okay, and now we are repeating this loop. And we are reading from whatever is in SI. Let's print SI. Info regs. In what was it? Info reg. Okay. ESI is this. Okay. We are taking the next byte and the next size, and if we compare it to 0, it should be equal. It's not equal to 0. I wonder if SI is modified somewhere in this creed. I think it might be, and I have not pushed it. Here it is. So I am modifying SI. Okay, so yeah, that's what happens when you don't take care of your registers. Alright, and then we up SI. And I think this might have been the problem. Exit. Okay, let's see if this works. Ah, finally. Alright, we have regenerated the image. Run disk. Okay, still not working. But at least we made some progress. At least it's not saying that it cannot load the image anymore. It's odd that it's displaying loading twice. which begs the question, what is it reading? All right, let's debug again and see. Okay. Continue. And let's continue. Okay, so we are at our bootloader. Okay, again. Okay, and now let's break. And now I want to do a memory dump. I want to see what is at address 500, which is where stage 2 should be. Am I writing stage 1 instead of stage 2, or am I reading the wrong sector or something? I don't know. Okay, so GDB dump memory. Okay, so we can use X and the address. Let's see what is at address 500. Okay, we need to dump some more data here. Wait, how does this work? You need not type the slash. If you use default, okay. So I need to use X slash, then N is the repeat count, so how many bytes to read. So how do you separate these? Oh, okay, so it's just the number. Let's dump, I don't know, 128 bytes in the format. X should be okay, and the unit should be in bytes at 500. Okay, why is it all zeros? That should not happen. No, that's not correct. Let's debug more. All right, let's continue, and continue again. And this should be the code for our bootloader. All right. Okay, so how can I jump forward? Okay, let me check if I got this right. Maybe I got the structure wrong, and that's why it's not working. Because what I think is happening is it's reading from the wrong place. That's my biggest suspect. Okay, so we are looking at this function. The data segment should be correct. Okay, so we have 1 byte, which is the size of the structure, which should be set to 16 or 10 hexadecimal. This looks good. Then an empty byte. Then 2 bytes, so a word, which is the number of sectors to read. Then 4 bytes, which are the segment and offset to the memory buffer to which sectors will be transferred. Oh, okay, the offset must be declared before the segment, so this is what I got wrong. These should be swapped. So I did get something wrong. Happens sometimes. What can you do? All right, so one more try. No, not GDP. We are confident that we have done the right thing. No, we don't want GDP. We want... Okay. It works. this took a long time, but it finally works. So what we're seeing here is a message from stage 2. Not enough memory to read fat. And the reason why is not enough memory to read fat. And the reason is because we are working with FAT12, so this driver works with FAT12, but here we are trying to read something else, which is probably FAT16 from what I've seen earlier. Alright, yeah, we finally have something that works. Now, okay, I think I will leave this for the next video because I've been streaming for like 4 hours already, and this is a lot of time. So next time we will clean up the code. I swear. This code was a bit messy. Today we wrote some messy code. We will fix it in the next video. In the next live stream we will fix it in 2 weeks. Yeah, so this is a little update that I would like to do live streams regularly, and my goal is to do it every 2 weeks. Now if something happens and I cannot do a live stream, then I will try to move it maybe to another day or maybe in the off week, but yeah, in 2 weeks. Do you want to have more live streams or what? The thing is that I also want to be able to work on videos. You know, I have kids and I negotiated with my wife to have like 2 days a week when I can work on this kind of stuff, and the live stream is on one of those 2 days, right? And yeah, I'm doing my best here. I also need some time to work on the videos because otherwise I'm just doing live streams. I won't have time for videos anymore, so that's the thing, that's why. Okay, but yeah, I'm very happy that this works. This was a lot of work. What is this? P1, I don't know. I think I messed something up at some point. This card. This is irreversible. Okay, I don't need this anymore. Okay, I'm just gonna commit all of this right now. Yes, that temporary file I will delete. I don't want to lose any important work from here. I don't need this, so discard. Okay, I promise that in the next video I will clean everything up. So, added support for hard drives in stage 1. Broken. I think I should create a branch for this because I don't want to break the code in the main. Yeah, I'm gonna create a branch. So let's create a branch for this. Branch, create branch, and let's just call it Bootloader 2.0. Okay. And now let's okay, all the files, yes. And publish branch. I hope I did not mess anything up. Let me see. No, byte OS. Okay. So branch bootloader 2.0, and there is the commit. Okay, you have the code. Yeah. Okay. Thank you a lot for watching my live stream. This was a lot of work today, and I did not expect it to take this long, but it did. I also wanted to do in this live stream, maybe to try to cover like doing some stuff in stage 2, like adding support for FAT16, FAT32. Also, another idea that I have is to basically create a configuration file that you can use for stage 2, so you can specify where the kernel is and a lot of other stuff. So yeah, a lot of stuff I have planned for this Bootloader 2.0 series. Let's call it that. Thank you a lot. Do you have any questions? Let's see the chat. If there are any questions. I've followed the chat until now, so... But if there are any questions before ending this, quick Q&A. If there are any questions... Okay, I don't really see any questions so far. I see a lot of suggestions, I see a lot of... Okay. I should use the Intel syntax. Yes, I am using the Intel syntax. GDB is not using the Intel syntax. The code cleanup. Okay, if you do the code cleanup, please do a live stream of you doing it. I will link to it from my channel, but I kind of want this assembly flavor Intel. Okay, you can do that in GDB. Nice, nice, nice. Okay. There's not a lot of work in cleaning up. I mean, basically, I would rewrite these files, these shell scripts, maybe in Python to make it a lot cleaner. The ugliest part, I think, is this. We're literally trying to write bytes to the file using bash, which it's not made to do that, but you can do it with some effort. But whatever, it works. So, all right. And what else? In stage 1, I think the code is mostly okay. Yeah, I think it's mostly okay. Maybe just rename the functions a bit, order them a bit more logically, maybe add some comments, maybe, I don't know, this stuff is a bit... Okay. Let's see what other questions we have. Yeah, so I will accept your pull request to do the code cleanup if you do a live stream about it. Okay? And I will link to it. Because I would like people to basically see all the code that goes into this operating system. And that's kind of my goal. That's why I have not accepted any PRs. I have a PR here. Somebody wanted to add some support for a couple of things. I have not accepted it, and this is the reason. I want all the code that goes here to be on YouTube, on this channel. If you make a video about it, or you make, I will link to it, and I will accept your pull request. Deal? Is that a deal? Okay. Okay, that is a great idea, to use Intel syntax. Okay, I will add it to the GDB script. I will test it if it works, and... Okay, for Docker. Yes, Python is great for scripting, I agree. Docker is great for reproducing builds, and that's the reason why I would like to use it. Because right now, the way this script is set up is some people are running from Mac OS, some people are running it from Windows. Maybe some people are trying to do the build from MinGW. I don't know if anyone does that because it's a lot of work, but whatever, who knows. I've noticed that there are differences even between for example, I have a server that sometimes I do development on, so okay, it's not Alright, and it's using OpenSUSE, and in OpenSUSE some things are different. For example, mkfs.fat, it's not in the path, it's in USR sbin, which is only in the path if you use sudo. So yeah, there are many minor differences between various operating systems, various distros of Linux. And using Docker, you can basically create a build which can be reproduced every time. we can create a Docker image for the GCC compiler, for the cross compiler. So, and having people pull it from the Docker hub instead of trying to build the compiler themselves, that will save a lot of time, and I think it's a great idea. So yeah, I will do Docker in a future video, in a future live stream. I don't know if it's gonna be the next one. I don't know yet, but I will do it. Okay, here's a little tip before you exit. There's a very cool tool which I'm in love with, which is called Twin, and it looks like this. Does this remind you of anything? And you can create like many terminals. And for example, here I can use Midnight Commander, and I don't know, I can go to open some file like this one, and it opens up in Vim. And at the same time, I can use this other window to look up stuff like manual, I don't know, st printf. Okay, there we go. Yeah, it looks very cool. It kind of reminds me of those old Borland compilers. Yeah, it also reminds me of Tmux, but except that you have full mouse support. You can resize. You have... Okay, this is not a maximize button as I expected. This is the... basically to bring it forward. It doesn't focus it. It doesn't bring it forward when you focus it. Which, I don't know, it can be handy sometimes. Yeah, I think this is a very cool terminal. I love this. I'm in love with this tool. But there's a bit of a catch. I haven't seen it in official repositories. Twin terminal or something. Oh, come on. SourceForge. That's where it was. Text mode window. Okay, this is the one. And to install it, I basically had to clone the repository, this GitHub repository, and build it. There are build instructions here. It's not super complicated. You just run configure, make, and then sudo make install. That's basically it. It's not difficult, but yeah, I haven't seen it in official repositories, but I think it's a very neat tool. Okay. Is that what you're making the tutorial? Maybe, I don't know. I'd like to do graphical mode. That's my plan in the future, to do graphical mode. I will do memory management. I will have the full videos for memory management. I will do the task management and task running, multitasking, all that kind of stuff. User mode. And after that, the plan is to do a couple of drivers, like keyboard, mouse, and what else? A couple of drivers. And then I will do the graphical user interface, because... No, I forgot about something. I forgot about the VFS. The VFS is also pretty important for graphical interface, because in you're gonna basically store a lot of stuff in files, and yeah, you kind of want to have file access when you do graphics. You want to load images, you want to load configuration files. There's a lot of stuff that you want to load from disk. Okay. Yeah, thank you for all the support, guys. I'm very glad. Yeah. We will see you next time, I guess. Thank you a lot for watching the stream, and we will see you in 2 weeks, or if I manage to edit that video, maybe sooner. Okay, thank you. See you next time. Okay. Signing out. Thank you, and bye-bye.